Welcome to Evaluating BFT, Comparisons and Trade-offs. This is an explainer brought to you by the Foundry at Forge College. I'm your host, and today we're doing a real deep dive. In our last session, we looked at the literal nuts and bolts of Byzantine fault tolerance. Today, though, we're putting on our hard hats and conducting a highly structured engineering design review of these BFT blueprints. We're going to see exactly what painful mechanical trade-offs you have to make when you demand absolute network safety. Because, in engineering, just like in life, absolutely nothing comes for free.
Okay, let's dive right into this. Here is our agenda for today's design review. First, the bottleneck problem. Second, comparing finality models. Third, throughput and latency limits. Fourth, the math of messaging. And finally, real-world deployments.
Section 1, the bottleneck problem. Safety versus throughput.
So BFT protocols achieve this literally legendary safety by forcing nodes to tightly coordinate with one another. But that safety comes with a pretty heavy physical cost. Just look at the math here. N must be strictly greater than 3F. This is basically a core law of physics for classic BFT. To tolerate F number of malicious nodes, your total network size, which is N, has to be strictly greater than 3 times F. This single equation right here is your baseline. If you want to survive bad actors, you absolutely must scale up your total network size and demand massive supermajorities just to outload them.
And here is the unavoidable reality of that trade-off. Stricter safety requires larger quorums and way more explicit message phases, which directly caps your maximum throughput. If you demand stronger safety guarantees, say you want to ensure a transaction can never ever be reversed or you require complex cryptographic proofs, that mechanically forces your nodes to do a whole lot more cross-checking. They've got to propose, pre-vote, vote, and explicitly commit. Every single one of those phases adds inevitable latency to the system. You are quite literally paying for that rock-solid security using network speed as your currency.
Moving on to Section 2. Comparing finality models. When is a decision truly permanent?
This brings us to immediate finality. It's defined as a state where commits are permanently final without any risk of reorganization the exact moment a supermajority signs off. Think of this as the ultimate, irrevocable stamp of approval on our blueprint. The millisecond the required votes are in, the block is final. Done. No takebacks, no alternate histories. It's as permanent as handing someone physical cash.
Now compare that deterministic BFT approach with Nakamoto probabilistic finality, the kind you usually see in traditional permissionless blockchains. Over there is no global commit message. Your confidence just kind of grows over time as more blocks get piled on top. It's a bit like waiting for a check to clear, right? You just wait until you're pretty sure it's not going to bounce. Probabilistic finality leaves that messy risk of reorganizations entirely to the application layer, while BFT guarantees clean, deterministic settlement right there at the consensus layer.
Section 3. Throughput and latency limits. Finding the traffic jams.
So where are the physical traffic jams in these architectures? Well, bottleneck number 1 is leader serialization. In a lot of BFT designs, a single leader node dictates the entire stream of proposals. That leader's CPU and their specific internet connection become an instant ceiling for the whole system. If the leader is slow, everybody is slow. Then we have bottleneck number 2, all-to-all confirmation. When every single node has to receive, process, cryptographically verify, and store messages from every other peer in the entire network, the effective message processing rate completely bogs down.
Which leads perfectly into Section 4. The math of messaging, the reply-all nightmare.
I want you to really picture this. What actually happens when 100 network nodes all try to talk to each other at the exact same time? Imagine being an exhausted office worker. You send out a quick email update, and suddenly 99 other people hit reply all at the exact same moment. And then they all read those replies and hit reply all to each other's replies. It would be absolute unmitigated chaos. Your inbox would freeze instantly. Well, that is the exact mathematical nightmare of communication complexity we face in BFT networks.
And this brilliantly illustrates the severity of that exact problem. If we simulate the data, comparing a naive all-to-all approach against a leader aggregation model, the results are wild. At just 4 nodes, a naive setup has a perfectly manageable 12 messages. At 10 nodes, we're up to 90. But watch how this scales. At 100 nodes, a naive peer-to-peer setup generates nearly 10,000 messages for one single decision. The traffic explodes quadratically.
Now, compare that to leader aggregation, where a leader acts like a strict project manager collecting votes. At 100 nodes, only 297 messages. The difference is just staggering.
So the mathematical takeaway here is pretty stark. Naive peer-to-peer messaging operates at an O of n squared complexity, while leader aggregation operates at an O of n complexity. You save massive amounts of network bandwidth by using a leader to just collect and aggregate all those digital signatures. But remember what we said earlier. In engineering, there's always a trade-off. By doing this, you're trading off those bandwidth savings by concentrating the entire heavy lifting and verification load directly onto the leader's shoulders.
Section 5. Real-world deployment choices, matching design to environment.
When you're taking structured courses over at Forge College, we really emphasize mapping these theoretical choices to actual physical environments. Just look at this decision matrix. If your application requires absolute deterministic settlement, like, say, a bank doing cross-border compliance, you just eat the high communication cost of a BFT protocol to get that immediate finality. If your goal is a totally open, permissionless network where anyone can join, you choose Nakamoto and you deal with the fluctuating latency. And for a private, trusted server cluster where you only worry about power outages, you use CFT. You always have to match the mechanism to the environment.
Finally, Section 6. Key takeaways, the engineer's rubric. So let's wrap this up by consolidating this architectural review into 3 actionable rules for deployment. First, map mechanics directly to costs. Every message phase and quorum size acts as a direct tax on your throughput. Second, prioritize which safety or liveness guarantee you absolutely need, because you can't have maximum parallel throughput and absolute immediate finality without paying a massive hardware and bandwidth cost. And third, measure your operational constraints. 10 nodes sitting in a climate-controlled data center versus 10,000 nodes scattered across spotty Wi-Fi globally, that changes absolutely everything.
I want to leave you with one final kind of provocative question. We just saw the math, right? If optimizing our communications centralizes all that trust and processing power into a single leader node just to save bandwidth, at what point does a BFT network stop being truly decentralized? It's a really fascinating paradox to chew on. To explore these complex Web3 topics further, make sure you head over to forge.college. Keep analyzing those blueprints, and I'll catch you in the next Explain.